Hello ladies and gentlemen, welcome to this video about pendulums. We're looking into some of the physics surrounding pendulums and specifically shedding light on how this periodic time of a pendulum is calculated and introducing you to this formula which helps us to calculate the time, the period of a pendulum, of any pendulum. And before we get into some of the logistics behind this formula, let's just have a definition of what a period of a pendulum is, what a periodic time is. Let's say you have a pendulum suspended from a point, and that bob, yes, that's what it's called, the bob makes the pendulum a pendulum. And let's say you hold out that bob suspended pendulum at an angle theta, well, any angle. And you release that angle from point A. Let's say that angle brought that pendulum to point A. Let's call that point A, and you released it. Now that pendulum will travel to, let's say, and will cover another angle from the imaginary line of normal at which the pendulum was initially at an equilibrium, or in an equilibrium, and so it travels to point B and then comes back. It's a natural movement of the pendulum, and once it does this, once it makes the journey from point A to B and then to point A, back to point A, that is the periodic time. That is the period of a pendulum. And this formula over here allows us to calculate how much time that period takes. How much time is that period of any pendulum whatsoever? And by the very first glance at this formula, we can see that it does not take into account the mass of the formula, the mass of the bob, the material attached to a piece of string or whatever it is. So I was quite surprised at that, and I was also surprised to know that the length is only responsible for the alteration in the periodic time, which we will discuss in later, with other factors which affect the periodic time. But anyway, as mentioned, T is, well, I didn't mention this, T just means the periodic time, the time of the period. L is the length of the pendulum, and I need to mention a very, very vital point regarding the length and how we actually measure the length of the pendulum. And G is the gravitational attraction or pull, or the constant of 9.81 meters per second squared. This is something that I'm guessing will be given to you, but anyway, yes, so what you really need to do for this formula is just plug in the length of the pendulum, to be honest with you, and that's not a tough task at all, except from one thing over here. The length of the pendulum seems very basic, but it is absolutely important that you measure the length. The length of the pendulum, in this case, which this formula considers, is from the point of suspension to the center of the mass. This is absolutely crucial. From the point of suspension to the center of the mass. That's the length of a pendulum. It's not from the point of suspension to the very end, the bottom of the mass, as many would assume to be, quite naturally as well. However, it's not. It's from the point of suspension to the center of the mass. Right then. So, let's move on to further logistics. The period is measured in seconds, not something very complex at all. The length is measured in meters, so yet again, if you're given centimeters, convert that into meters, which is not a very tough task at all. I can make a video about that if you want me to, but it would be quite a useless video. Yes, as mentioned over here, the length of the pendulum is always from the point of suspension to the center of the mass of the bob. Right. Now that we know what the numbers, what the letters, these two letters stand for mainly, we can exemplify something below over here. Let's say there's a pendulum, a meter long, and yeah. So to calculate the periodic time, how much time its period would be, we just plug that 1 meter into the formula. So T equals 2 times pi times square root of 1 meter. As mentioned above, we always measure in meters the length of any pendulum from the point of suspension to the center of the mass, over 9.81, which is the gravitational acceleration. And our periodic time would be 2.007 seconds. What does that mean? It means that pendulum will take 2.007 seconds to travel from point A, when released from point A, any point whatsoever, and then travel to point B and then come back. It will take 2.007 seconds in these two oscillations, in these two natural fluvial oscillations. Now then, before we go anywhere, we need to mention, or we need to take into account, the factors which affect the periodic time, and the two factors which I was quite surprised which do not affect the periodic time are the weight of the object, the bob, and the angle at which it's held at. If you take into account the line, the normal line as indicated by this dotted line over here. So let's pretend we've got pendulum X and pendulum Y. Pendulum X is held, they both have the same length. Both are of the same length A. Let's say they're both of the same length A. And pendulum X is held at 20 degrees from the imaginary line of normal. And pendulum Y is held at 75 degrees, a considerably bigger angle, right? And they're obviously at two different points in the air, at the point they're held at, and we release them together. And if we record the periodic time physically with the stopwatch, you will get the very same periodic time for both of them. Therefore, through this, we can conclude that the angle at which you hold the pendulum is irrelevant regarding the periodic time. So moving on to the next one, the weight, the mass rather. The mass is also irrelevant. Let's say you've got pendulum X and Y again, and they're both of the same length A, and they both have they have differentiating angles at which they're held at. Let's say they're not. Let's just assume they are for this case. And pendulum X is a kilogram massive, and pendulum Y is a ton massive. Would they still have the same periodic time? I mean, come on. I first assumed that pendulum Y, it's a ton heavy, and the gravitational potential energy would be much bigger over here. So this, from my point of view, I thought that this would take longer. However, even that's irrelevant. Would you believe it? Considering the periodic time of a pendulum. So that leaves us with the length of the pendulum, length A. So long as they are both of the same length, the periodic time they will give to us will be absolutely identical, regardless of the fact that whether the angle they're held at or the mass of the bob is a world apart. They will give us the very same periodic time, and that is very, very fascinating, and that's the beauty of the formula and pendulums in general, I suppose. And we can conclude from this, rather as Galileo once concluded, which I will also get into more detail about how he figured this formula out. Yes, he did. Galileo concluded that the length decides and judges the periodic time. the bigger the length, and I'm sorry I haven't mentioned this somewhere around here. Oh, I have. It's over here, very, very vaguely, but only. But anyway, so yeah, it's the length of the pendulum. The bigger the length of the pendulum, the bigger the periodic time. So let's say this was 9.81 meters. Let's say this pendulum was 9.81 meters. So we just plug in t equals 2 times by pi. In fact, just write down here, to be honest with you. Just calculate it before you. So t equals 2 times by pi times by 9.81. Yes, do you want to have a guess why I picked 9.81? Because I just like the number, to be honest with you. So we just have 2 pi times by 1, because 9.81 divided by 9.81 is 1, and the square root of 1 is 1, so 2 pi times by 1 equals 2 pi seconds. So I hope you understand, ladies and gentlemen, that the pendulums are very, very useless. No, only kidding. They're very interesting, and the only thing you really need to require some, knowledge over are the measurements, what kind of units they're recorded in, and certainly this very, very important rule of measuring the length of the pendulum from the point of suspension to the center of the mass, and yet again, knowing that only the length is proportional to t. It should be the other way around. I'm absolutely jet lagged right now. I apologize for this. It's the periodic time. T is proportional to L. Thank you very much for watching, and before I send you away, I still need to keep you in a bit more misery, because I'm going to inform about the formula's history. This formula is said to be about 300 to 400 years old, and the original founder of this was the creator. Was Galileo Galilei, the mastermind himself, the godfather of, the grandfather of relativity, as they say. There are two theories themselves behind how Galileo arrived at this formula, and what really interested him to calculate, to discover and, delve into physics regarding pendulums. Both of these stories are narrated by his student Viviani. Viviani quotes that, he states that Galileo was very fascinated by the movement, the oscillating movement of the chandeliers. And he always wondered whether there was some kind of, relation between the length or the mass of the object, or the pendulum, or the angle theta it's held at, which affects the periodic time. And this really inspired him to delve into the physics behind it, research behind it. And the second theory, which I find absolutely ridiculous, to be honest with you, is the one where Galileo was really fascinated by the periodic movement, oscillation-like movement of musical instruments, which I have no idea about. It's just something I researched into, and Viviani narrates that Galileo's father was a musician, and whenever Galileo used to practice music with his father, he was really fascinated by some periodic movement. It wasn't called a periodic movement; it's just called a oscillation of some particular instruments, which I have no idea about, by the way. I believe the first theory to be much more accurate than the second one. And I'll leave you there, ladies and gentlemen. Thank you very much for watching. Please like and subscribe, and I'll see you in the next video. Thank you.